I have again the pleasure to introduce a special person. I mean, that's what we all are, I suppose, you know, going to Mars, doing space industry, doing space research. That means something. Skip Hatfield, I found out, is a practical man by his own account, as he tackles not his just big NASA projects, but also do-it-yourself projects in his home. In short, a man after my heart, because I love and take pride in doing do-it-yourself projects at home too. It might be very clear that we need practical-minded people to go beyond ISS. And having Skip heading the development of complex systems for human spaceflight gives me therefore confidence that however hard it is going to be, we have the best man at the helm. Skip, introduce your own panel, please.
Well, thank you very much.
You're welcome.
Well, good afternoon. I see we managed to empty the room, so I guess that's going to make the question and answer easier at the end. So, you know, it's a tough act to follow the group that we just had. It was a very august group that talked a little bit about setting up what ISS is all about. And I'm going to talk a little bit about where we're going from here into cislunar space. We have a very august panel with us this afternoon, a bunch of very experienced folks. You know, they've all, as you'll see in their presentations, they have some great ideas. You know, we have David Smitherman, who's here from the Marshall Space Flight Center, and his day job is to, he's the manager of future human spaceflight projects and the Advanced Concepts Office of the Marshall Space Flight Center. Many of you have known him for many years. He's done a lot of studies and has a lot of great knowledge and insight into the kind of things that we're going to need for the habitat systems as we go beyond the low Earth orbit system. Matt Duggan is with the Boeing Company. His day job is he's managing the integrated analysis efforts for the ISS program. And then his sort of part-time job, which is why he's here, I suppose, is looking at the advanced development concepts and looking at future things that we'll be doing in habitation. And then finally, we have Josh Hopkins, who has the title of Space Exploration Architect at Lockheed Martin. He has the honor of leading a multidiscipline team that looks at all things space. You may remember him from some of his earlier work, like the Plymouth Rock mission that was proposed by Lockheed a couple of years ago. He also has, in the past, worked on the lunar landers that we were working on under the Constellation program. So we've got a great group here today, and you'll hear a lot more about their efforts here in a moment. So with that, I'm not going to use any charts today. I know that's unusual for a NASA guy because we live by charts, right? But since charts really, you know, just give you something to distract from me waving my hands, you know, maybe you'll, you know, talk to me or see me more as a person. As you see, the things that we've done in all day long today, you've seen the chart, the spiral chart that shows our progression from low Earth orbit outwards. I thought about putting that chart up, but I figured you'd seen it enough times today. You may remember the major elements on it, which are, you know, the Earth-dependent, the proving ground period, and then Earth-independent. The proving ground period is a lot of what we're going to talk about today, because as we're moving out from low Earth orbit, it makes sense for us to incrementally prove things that we're going to need to do to go to Mars. Immediately jumping into a 1,000-day round trip to Mars is a pretty daunting prospect, and having the systems that we can do that is pretty challenging right now. Just the little things like closed-loop ECLSS, you know, are a challenge today to prove that they can operate in a low logistics environment and be reliable for that long a period. So we have some work to do. ISS brings a big part to that as a foundation, you know, in the initial periods here, the Earth-dependent periods. We have a lot of things that we're doing there that are paving the way. One of the things that many folks don't know, it's part of my day job, is we're converting the docking systems on the U.S. Segment to be compliant with the new international docking system that a multinational consortium has developed. We'll be using the commercial crew vehicles to demonstrate that technology and prove that we have a good system that allows any spacefaring nation to dock together that's compliant with that standard. Should really reduce our integration times for those kind of efforts. We're testing advanced systems on ISS today. We'll be looking at improvements to ECLSS and some of the other kinds of things like that. The advantage of doing these things on ISS, you saw the fact that we're only 2 days away in a round trip, you know, basically from Earth to ISS. That allows us the opportunities to repair those things with a pretty regular logistic stream and upgrade them as we need to. So that helps us a lot, not having, if you're 6 months away and something breaks to get a part, it's not exactly like going to AutoZone and saying, gee, things are great. So being able to do those in ISS is fantastic. And lastly, the last presentation that you heard a little while ago, the things that we can develop in human health and studies there in low Earth orbit are really fantastic. We'll have a much longer or larger crew size, over a longer duration than we can ever hope to have in Mars missions for learning more, as well as even in the cislunar period where we expect to have, fairly short missions early on. Which leads me a little bit to what my part-time job is. I've been tasked to develop the requirements for the habitation systems that we'll use in the proving grounds to help demonstrate, our capabilities of going to Mars. So we're working on big parts of that today, and there's really kind of three elements that we're working on to develop those requirements. One is we're working closely with the international partner community. We've had a series of meetings ongoing with them to understand what their strategic objectives are, to be able to mesh those with our nation's objectives to have a cohesive space exploration plan that leads to Mars. And so that's been a great effort so far. Much like ISS, that's provided the framework for these discussions, but we expect that the partners will provide significant contributions to any effort that we go beyond low Earth orbit and onto Mars. We also have a number of internal studies that we're doing, and the most recent thing that we've started up is we've begun an updated reference design to inform the requirement set that we've been working on. Today we have a draft level 1 set of requirements that we have that we're reviewing internally, and this reference design will inform that knowledge more and help refine those requirements going forward. And then there was a question earlier on about the next step BAA. That's the third leg of this stool that we're using to inform these requirements. By using this BAA and getting industry involved and getting their ideas about what habitation systems could look like, that will help inform the final set of requirements that we'll be able to use to develop detailed requirements for the individual elements that we need going forward. So we're already working, as you know, and the big elements of the space transportation architecture are in place and being developed, the Space Launch System as well as the Orion system. The next big thing that we need to do if we're going to go long distances is have the habitation systems. And that has to accommodate the larger volumes that we're going to need for crews to be healthy and psychologically fit. It has to contain all their consumables and all the things they'll need for a 1,000-day mission. So there's a lot of things that go into that next step. The proving ground period is a great time for us to demonstrate these capabilities, and the concepts that we're working on today call for us to begin in the early 20s with a set of missions that will be visited by Orion, obviously, to gain some early experience in cislunar space, leading to a series of longer missions, and we're going to capstone that. You may have noticed in the chart at the bottom in the very fine print, that spiral chart that we've seen, that the proving ground period has missions that start at 1 to 2 months and culminate in an approximately 1-year mission. The idea for that is we expect to have at the end of the proving ground period, when we're ready to declare that we're ready for Earth independence, that we will have conducted a 300-day approximate mission to a destination, a physical destination, basically simulating a one-way transit to Mars. So that's the objective that we're pulling towards. It's a daunting task to get ready for that. Into the 20s sound like a long time away. They're really not from a development standpoint, for those of you that have been in that kind of business, and I know many of you have. As we look at this kind of series of missions heading outward in proving ground, there's a number of things that we see that the habitat has to have as essential capabilities, and most of these are obvious to those of you that are in the room. Some of them maybe not so. One of you heard a theme on several times today is we're looking to make this kind of a system be reusable. One of the things that we expect would be a huge driving cost in any kind of exploration effort is the number of launch vehicles that we employ, as well as the number of systems that we fly. The fewer of those that you can do, the more affordable this becomes. So if you can reuse elements of this, you reduce launches, as well as reduce recurring cost of developing these kind of things. There's a corollary to that, though, because if you do that, now you have to have a resupply and refitment capability. So that's another thing that we expect to prove in this proving ground period is how we resupply and refit this kind of a system before we undertake that kind of long-term reusable system. We need to have obviously enough volume to support the crew's exercise needs, their physiological, and I already mentioned psychological needs, the stowage that we need to have their supplies, the consumables that we need, as well as any spare parts and that sort of thing, any science support. And this system ultimately is going to have to provide support to surface operations. And that kind of mission that you're talking about to Mars, if it's a 1,000-day round-trip mission, roughly a third of that is the transit outbound. If the crew then transits to the surface for roughly a year, then the habitat system has to be dormant for that long, and then be able to be reactivated when the crew returns, to the vehicle for that return to Earth. So we have to be able to demonstrate those kind of capabilities too, to be able to go dormant and restart. And as I mentioned earlier, we basically need to make sure that we can resupply and refit the system. So these are pretty daunting things that we're trying to do. And the last thing I'll mention on that is we want to avoid point design solutions. It's one of the things we get in the business of. It's a chicken and the egg thing oftentimes when you're writing requirements. The technical community always wants to know exactly what are we going to do with this thing, so we can write the requirements narrowed down to that kind of operation. If you say we want a generic capability to transit crews anywhere beyond the low Earth orbit, the community gets upset. Well, we don't know how to write requirements for that. What about thermal requirements about low lunar orbit? How are we going to deal with that? So we have to be able to develop, some systems and basically some ground rules that allow us not to have point designs and enable a generic capability. So that's the challenge that we're working on. And the group that we have here today is going to enlighten us a little bit about some of their thoughts about some of these things. And with that, we'll reserve questions to the end if you don't mind, and then we'll do that as a group. With that, I'd like to turn it over to David for his remarks, and we'll go from there. So thank you all.
Test. Okay, thank you. I've titled my presentation Deep Space Habitats. That's the work that we've focused on in our office for a number of years. And let's see. Okay, we've been involved with the Advanced Exploration Systems program for a number of years, since 2011. And so what I'm going to show you is a little bit of the work that we've done and kind of the path that we're on and some of the findings that we've had as far as exploring deep space habitats. What you see here is a collage of work that consists of studies that have then since been turned into technical papers that are available to the public, and then mock-ups of a lot of the work that has been done. We started off looking primarily at ISS-derived systems as far as the size of the habitat, and then we've moved on to larger systems that we call launch vehicle-derived systems. So you can look for this information through the NASA websites, through AIAA. A lot of the papers were published by AIAA. You can look for it under my name. Brand Griffin is an author on many of these papers, and it provides a lot of interesting work and insight as far as what we've found so far. You'll see in the graphics here along the bottom the mock-up work that has been done. We've used HAB-size modules, nodes, and MPLMs, and gone to recently to a large volume diameter module, which is representative of SLS diameters, an 8.4 meter. So that's available, that information was available out there also. And then towards the end of the chart are several configurations that we've looked at, most recently honing in on Mars vehicle habitat design. So most of the early work was focused primarily on cislunar space, missions that we might do to support the asteroid mission, and then more recently, what these final configurations might look like for a Mars transfer vehicle. So the work that we've been focusing on has included what we would do at space station. Some of the early studies that we looked at actually considered doing the assembly of the elements at space station before we transferred them out. So we have information on what it takes to do that. And then also considering what the other uses of a facility might be in deep space, being in the cislunar environment. So we've looked at Earth-Moon L1, L2, and the distant retrograde orbit. We like the distant retrograde orbit because it is where the asteroid mission is currently planned to go, and it's a very stable region. It helps us out on the design of the propulsion and control systems for the habitat. And then, of course, using one of these types of designs to eventually go to Mars. We've also looked at a variety of launch vehicle configurations. This shows the latest work that we've considered for SLS. We've looked at both co-manifesting payloads with SLS, with the Crew and the Orion module, and also doing dedicated payload launches. And so there are 4 vehicles that you see here, representative of kind of some of the latest things that we've looked at. The first one, going from left to right, looks at co-manifesting basically an ISS diameter size module. And what we found that we could fit in the payload bay that's provided below the Orion capsule is something on the order of module between the MPLM and the HAB size module. It's actually a stretched MPLM. So instead of having just 4 crew system racks or 4 bays of racks, you could actually put 5 bays of racks. But for the early flights of SLS, the study that we did was looking at basically a 10 metric ton limit on that capability. And so what you find is that you can get the actual module up, but you have to do a lot of outfitting on orbit. And so it's similar in a way to the way a number of modules were outfitted for the ISS, where you would launch a 10 metric ton module, you would outfit it, and by the time you're finished, you have something more on the order of 15 to 20 metric tons. And so that's what you see here. And this work and the next one was actually done in some recent work that Skip asked to be checked out and to looked into, and so we help with that activity. The second one uses a larger diameter module. It's 5.5 meters in diameter. It fits under the Orion, and it's basically the same diameter as the Orion aeroshell that fits around this service module below the Orion. And so we took advantage of that diameter, came up with a little bit different design, different mass statements, and it has some advantages as well. So that information is coming available also. Then the last 2 configurations looked at the full diameter of the SLS using a full 8.4 meter diameter module, one smaller version using the ICPS for the upper stage, and then a larger version using the EUS exploration upper stage for delivery. And so those have been looked at. They're interesting concepts that we'll show you a little bit more on that. Next. Our early published work on mass properties is shown on this chart. This was published back last fall in an AIAA paper, so it is available. And one of the characteristics that we found for the cislunar space vicinity out around the moon is that for your 4 crew 180-day missions, your ISS modules, when they're grouped together as small modules, actually turned out to be a larger mass than the one large module for that vicinity. So we can go with the smaller modules. You're looking at on the order of 45 to 48 metric tons. The single module design was starting to prove more beneficial and actually helped to trim some of the mass down in the mid to upper 20s, around 30 metric tons. So we put together a chart that tries to start to explain that. This is a mass and volume chart that you'll find in that particular paper that I was referencing. And it's showing, for starters, an example of what Skylab weighed and the amount of volume that you got with Skylab. And so, because Skylab was basically a single module, you have a relatively small mass in comparison with a very large volume, open space that's provided. When you move to Space Station was a different concept. We deliberately chose to launch mini modules with a lot of interior outfitting that included a lot of laboratory equipment. And so you have a very high mass by comparison. You have a very large volume also when you add the volume up, but the mass represented in red is very high in comparison to what you have for the ISS, the Skylab module. Then you see two groups of studies there where we looked at the ISS modules grouped together in comparison with a larger single volume module that could be launched as a payload on SLS. And you can see that by and large the masses stayed about the same all the way across, but when you start to look at the volume that's available, it really jumps up. So basically for the same mass you can gain quite a bit of volume in these cases by going to a single module concept. So these are some of the configurations that we developed just recently, looking at the different architectures, now going with a 4-crew 1,000-day mission. This is considering a long mission duration where you might have 500 days out at Phobos or on the surface of Mars. So by the time you go out there and back, you're looking at a total of 1,000, on the order of 900 to 1,000 days. So for a 4-crew 1,000-day mission, we found that that if you went with the ISS module diameter, you'd basically need 3 modules to do that mission. And that's a couple of HAB modules and a large logistics module to carry along with you. When we then stepped up to the 5.5 meter module that I mentioned to you, we found that we could actually pick up a little bit more volume and then just go with 2 modules. And so this was an interesting study and made for an interesting comparison. And then finally, with the 8.4 meter diameter module, we found that we could just do essentially the same mission, have even more volume available to the crew, and have just the one single module. And so the masses are not listed specifically. They will be published later this year in an AIAA paper. But you can see that the red bars for those 3 vehicles actually drop slightly for the mass. So the mass actually comes down a little bit as you go from a 3-module set to a 2-module set to a single module set, even though you're increasing volume all along the way. And so this is an interesting finding and a potential benefit for taking that approach. In addition to looking at the modules, the launch vehicle configurations, we also have been doing work on interior configurations and layouts. And this is where you get into the mock-ups that we've been studying. This is a comparison or a look inside the Skylab module in comparison to a look inside of a HAB module. And you can see the red circle, that's the circle around a crew member. So I tried to put them about to scale as far as the actual volume of the interior that you see in comparing the two. So the original Skylab was quite large inside. It was on the order of 22 feet. The space station is down around 14, 15 feet on the interior modules. So my final chart and looking at interior configurations, everyone mentioned that, hey, there's a big difference between work at space station and work at doing a Mars mission? What are those differences when we want to prove that out in the proving ground in cislunar space and try to identify those differences? We're trying to translate those differences into design. What are the differences in the design? And so some of the things that I'll point out here is on the module itself, the single module that you see on the right starts off by putting the crew quarters right in the middle. And that is to help pick up the maximum amount of protection with all of the systems and subsystems and stowage around the crew quarters for maximum radiation protection. So that was a start at the concept. Another learning point is that Skylab, which I showed the interior of, was actually a vertical orientation. In Space Station, we've been going with a horizontal orientation where everything is lined up along the walls. There's been a lot of space savings benefits to that, good organizational and efficiency benefits to laying things out horizontally. So we've proposed to do that in this large module also by putting it on 3 floor levels, where you have the primary crew quarters in the middle, you have on the upper level your food and galley, and then on the lower level an exercise and systems area, subsystems area for the vehicle itself. And then in the lower chart, the lower looking across is a comparison of the interior subsystems with the way we would lay out subsystems for a future mission. Basically, on Space Station, everything is in racks. You can replace the racks and do upgrades by replacing the entire rack. That's been very beneficial for Space Station. But for deep space habitat where you're going to Mars, you need access to those subsystems. And so we're proposing a pallet layout. Since you have a larger volume, more room to spread things out, let's spread the subsystems out on pallets where you can access the individual components, be able to change them out and do maintenance, do checking along the way. So that's some of the things that we've learned, and we tried our best to document that and get the word out. And so we're hopeful as things move forward with industry to help us actually develop the real habitat that they'll take a look at these concepts and fold that into their knowledge base as well. And thank you.
Thank you, David. And with that, Matt, you're up next.
Thanks. Thank you, Skip, for having me. I am going to show some charts. I'm not quite broken free from that, but I'll try not to describe the words on them so to get closer to the ideal here. I will be echoing some of your sentiments. And you'll identify exactly where they are in the way. So we've talked a lot about the proving grounds here, and I'm not going to go over what that really means. I think we're all well familiar with that idea now and what NASA means when they say that. I'll say that we totally agree with that idea. It's the incremental approach. You're building a path out from Earth to Mars, and you're learning along the way. As was pointed out yesterday, it's kind of a false dichotomy to look at that as an either-or concept. We're either going to the moon or we're going to Mars. No, we're going to Mars through the proving grounds, through the lunar space, and we're learning as we go. And as we build further outward, we are evolving our capability. You're building modules that you can scar for the future. You're not just going to use it now and throw it away. It's useful now, and then in the future, you enhance it in some way. You put in systems you may not even know about today, but you've built the capability in to swap out easily in a pallet concept or something like that. So some of the key assumptions here, we live and die by our assumptions in the absence of actual requirements. Again, to echo Skip, as an engineer, it's always difficult when you're trying to go design one of these concepts and you don't have requirements to build from. So you build in a lot of assumptions. You have to assume the mission you're building for. One of the key assumptions that we've struggled with is the long dormancy period. When we have a vehicle, we're going to put it out there and then essentially abandon it for a long period of time. You go for 30 days and then it's going to sit for more than a year. There are some systems that just will not deal with that well. A lot of the avionics systems, the electronic systems, those are relatively easy. You can turn them on and they'll come back on. What we found in ISS, though, is that systems that have moving parts, and particularly systems that move fluids, such as water or air, They don't like to sit dormant. That is much more of a problem. You have technical terms like biosludge or ooze building up inside your system, and you know, we've lost hardware to that kind of thing, and now you're letting it sit for more than a year with no human intervention. And also, as we've observed yesterday, life finds a way. We've found life in all sorts of ISS systems where we really didn't expect to find it inside the cooling systems, inside the ECLS systems, and that's bad for the system. It builds up and then stops your system from working. So that's an important assumption that we're going to have to build into our system. We're going to have to figure out a way to solve that problem. And most of our systems now are assuming that we're getting past that. But I will note that for ECLS in particular, we're going to need some improvements in our existing technology to get there. The SLS co-manifest capability that David alluded to. I'm going to talk a little bit more about that in a second, but that is an important capability right now. It allows us to put a piece of cargo, a piece of infrastructure, if you will, on every single SLS flight. Instead of having to move that onto a dedicated mission, you can get it out there when you already have the crew there. They can deal with it immediately, and you can also use it to extend the Orion mission. I'm going to skip some of those. The next one I'll call out is the international contributions. Any architecture we build has to be open enough to allow the international contributions to come in when they're necessary. We may not know what those are now, but if you build a closed architecture that really doesn't have any ability to grow, any ability to change, then you've locked out some people who may want to participate later. If we develop something now that has lots of opportunities, once it's started, other people may join, and we have an open enough concept of systems that we can add them in easily. The evolvable systems are important in the sense that we'll change over time. If you know what you're already going to do, I have a system now that is a 10 kilowatt power generation system, but I already know how I'm going to upgrade it to 50 later for SIP. That's important to know and build in from the beginning, and the same with other systems as well. And then finally, Orion as a contributing element. Orion does bring a lot of capabilities into cislunar space, and some of the concepts that we've had in the past tend to just have it as a parked at a space station in lunar orbit for 30 or 60 or 90 days. And that ignores its capabilities. We need to bring those capabilities into the planning and use them as we're there. Probably one of the more obvious ones is the toilet. Why duplicate a toilet when you're already there? The Orion's only going to be there when the crew is there, or stated the other way around, however you want to say that. So you don't need those systems when the crew isn't there. The capability of Orion also as a tug will be important. It can move elements around, and with the co-manifest capability, if I can use Orion to move an element around that I'm delivering, then I don't have to have that same system necessarily in the element. That saves mass and avoids duplication overall. So some of the important exploration enablers that Boeing sees. We have a large amount of experience now with various operational systems in space, and that's the catalog of hardware that we're using to produce the various concepts we do for cislunar space and Mars, at least as a starting point for some of the further out Mars work and as a very near build-to-print catalog for the near-term stuff. ISS, obviously, operational system today, that is where the majority of all of our human spaceflight experience lies these days, and so we depend heavily on that experience, and in some cases on those systems themselves. Not all of the ISS systems are directly translatable to cislunar space. Some of them will not operate for reasons such as radiation and so forth, but they can still inform us by what we've learned from them. Commercial satellites are also a big focus of ours now. We had somewhat of a divide between the human and the commercial spaceflight systems, but we're trying very hard to bring those together and draw on the satellite systems. The major advantage of the satellite systems is that they're already designed for the deep space environment. These are geosatellites, and they can handle the radiation that we'll see out there. So some of their avionics and power generation systems are pretty much immediately importable into a human spacecraft for cislunar space. So putting all of that together, we've had now for a lot of years, large history of various cislunar vehicles, and they all have followed the same basic pattern of you take an ISS-derived habitat using that module technology, and you add that to a satellite-derived bus, and you end up building a fairly capable spacecraft. And as you can see from others as well, I think we've all kind of coalesced on that idea now. And have figured out that that's probably the near-term solution for cislunar space. So using all that, we've looked at what we would classify as large and small habitats. The small habitats are getting into the co-manifest space where we can launch a small element with every single Orion. And so with every single manned mission to cislunar space, you're adding to your cislunar infrastructure. But we've also looked at the larger habitats as well. You may eventually want the efficiency that a large habitat gives you, and so you will choose to pay for a dedicated SLS launch and take that large step forward rather than the smaller incremental 10-ton. So overall, we've been focusing on developing that Earth-independent capability, how we get out there in a way that is always evolvable to Mars, always with the focus on Mars. So I said I would talk about the SLS co-manifest capability. David introduced it, but this is a really pretty exciting concept. A lot of our early, what we call the Block 1 stuff, had only an Orion, and then you had to have a separate mission for your cargo. By being able to launch cargo on each SLS mission, you're realizing a huge cost savings there. First of all, because you don't have to have the additional launch, and then also you have that cargo immediately available for the crew to use. You can use it to extend the Orion mission duration, and you can use it to build your infrastructure. It's also immediately there for the crew to outfit, to activate, to do whatever they need to do. You don't have hardware that's waiting for the crew to come do something to it. So there's a couple of things that enable that. One is the NASA Exploration Upper Stage. That's a larger upper stage that will give more launch capability. There's also some improvements to the core vehicle as well to get there. You can use innovative trajectory designs, low energy trajectories to mean that you can move more mass further. And then Orion mass reductions, I do have to say, you got to control your weight. No offense. But speaking as, you hold your mass in reserve, and then everyone starts to come forward. So once we build this SLS co-manifest capability, I want to protect that for the true co-manifest and draw the line for Orion there and say we need a 10 to 12 metric ton capability for the SLS for this co-manifest thing to work. There is a tipping point as that mass decreases where it becomes less and less useful and finally not useful in terms of building infrastructure in cislunar space. We can argue about where that is, but I would say it's in somewhere in the neighborhood of 8 metric tons, and below that you just really can't build a vehicle that's going to make a substantial contribution in the long term, a permanent contribution to the cislunar infrastructure. So the capability build-up, I don't intend that to be a Boeing plan for the exploration missions. It's more of to illustrate the idea that with the co-manifest, each time you are adding an element, you add a habitat, you add a logistics module, you add another habitat, and so forth. So every Orion mission, you are delivering something useful, and you're aggregating this larger and larger vehicle in cislunar space that is building you toward Mars. And each mission then, when you deliver more large logistics and a larger vehicle, that enables the longer duration. You can go from 30 to 60 to 90 to the nearly 1-year mission. Over time, you might even take that vehicle to Mars. That could be your Mars vehicle that you're already starting to build there early on with these incremental 10 metric ton missions. So the small habitats, I will agree, again, with Dave, that small habitats are inefficient in the sense of the mass and the volume. The larger you make your volume, the more efficient the amount of mass you have to spend on the structure is. The surface area is, the ratio there is getting more and more in your favor. So you want to, from that perspective, you want to make the largest habitat you can. On the other hand, that is constrained by the amount of launch mass you have available, the amount of volume you can fit in your rocket, and the amount of money you have to spend on the habitat at any one particular time. So again, that's where the 10 metric ton habitat has a place here. You can co-launch it with Manifest, with Orion, and so you're not adding additional launches to your Manifest. You're not having to pay for an additional SLS launch or some other heavy launch. You are using a launch that you've already planned to have regardless. The small habitats also give you a better cost distribution overall. They cost less to produce, so we've talked a lot about the budget here. They contribute to a flatter budget overall. By having smaller elements over more time, you've flattened your budget and can have a more steady and plannable budget overall. On the other hand, the large habitats, they are more effective, more efficient in terms of the mass and volume. You can put everything in at once. You only have to have one set of docking systems rather than multiple docking systems, for instance, as you build up small habitats. They are maybe simpler to design in some ways, maybe not, but you can put more engineering into a single project, which is in some ways attractive from the engineering point of view. On the other hand, they are a much bigger investment at a particular point, and so that's going to give you a budget that is more spiky, if you will. You're going to have to put more money out, and that can be unattractive possibly, and also they will require a dedicated SLS launch. So there's pros and cons on either one of those elements, and we're trying to explore both of those and have habitat designs that live in both areas. And so again, to go back to the requirements, I'm not going to go over those individually, but these are the kind of things that we have to assume each time we do one of these concepts. And I just have to point out that any one of these concepts is largely based on the assumed mission that we don't know yet. And so what's really great about the focusing in on the proving grounds and getting closer and closer to the real mission, that is where we're really going to start to inform what the true engineering requirements for these vehicles are, and go from concepts to much realer vehicles, things that are really trying to address the mission using the systems we have. And so finally, again, we talk all about the proving grounds, but it's focused on Mars. That's where we want to go, and we always have that in our sights as the ultimate goal, down to system by system. How is this getting us to Mars? Why would we choose this system over this system? Well, this one may have more applicability in Mars. So we look at that in our solutions today, and that is obviously our ultimate goal. So thank you very much.
Thank you, Matt. And
Thank you.
with that, brings us to our final presenter, which is Josh.
Okay, so I have the dubious honor of being the last speaker of the day. I'll try not to let you fall asleep. I'm going to be talking about some of our thoughts on not only what we could build as a lunar outpost, but also why a lunar orbiting outpost would be worth doing, and to try to address that from several different perspectives. We've talked multiple times during this workshop about these incremental proving ground missions, but we haven't necessarily gone into much detail on them, in part because everybody's more focused on the long-term trip to Mars. But I think it's worth re-emphasizing that actually part of the reason we haven't talked about these orbiting outpost objectives very much is that there is already widespread agreement on them. They're not particularly controversial. And this was particularly interesting to see at the Space Exploration Conference in Strasbourg, France last fall, when agency after agency got up and talked about the idea of an outpost or a orbiting habitat or an exploration augmentation module, whatever program name you want to give it, as being a good idea. So agency after agency said this, and then the companies got up, and Lockheed Martin said it, and ATK said it, and Boeing said it, and Thales Alenia said it, and Mitsubishi said it, and Energia said it. There was essentially a uniform consensus that something like this is a good idea. Now, there's differences of opinion about what exactly it ought to look like and who should get to build it, but the general theme of building one of these and some of the basic purposes that it would be used for, there's a pretty good agreement on that. Now, let me talk about two specific perspectives on this that may not be obvious. One is the Mars community. Why does the Mars community believe that a lunar outpost is a good idea? This came up in multiple Affording Mars workshops over the past few years. And essentially, the thinking is we cannot take that giant leap to a 1,000-day Mars mission straight from a ISS type environment. We need something that is on the edge of deep space where we can not just study and simulate, but practice operating on the edge of our supply line, where we are too far to come home quickly in an emergency, but not so far that you can't come home at all. There's a lot of things you can study, and you can imagine how you would tackle them if you didn't actually have to tackle them. But when it really comes to building a spacecraft, you're going to end up with these difficult engineering programmatic decisions about what safety features are worth incorporating and which ones are just too hard for the benefit you get from them. And you really only figure those things out when you really have to solve those problems. So the Mars community in general has supported this concept. Another community that has been supportive of this is the international community. And we haven't really had much of an international perspective at this workshop. We have tended, as Americans tend to do, to show a whole bunch of American concepts and then explain that the reason they're affordable is we're going to get other countries to help pay for them, without really incorporating what those other... So when you look at this from, for example, an Italian perspective, a Canadian perspective, the perspective of other agencies, if we struggle to just barely see how Mars exploration can fit in the NASA budget, imagine what this looks like to the head of agencies or the minister of government in a country that spends 1/10 as much as NASA does on space, or 1/20th or 1/50th. Mars looks just way too expensive. Human Mars landings look just way too expensive. The other thing to think about is what are the priorities and the objectives of these other space agencies, these other countries? Well, they each have different technology specialties or areas they would like to get better at. They each have different strategic and geopolitical goals, but one goal that almost all of them have in common is they would like to fly a native astronaut on these missions. Now, the problem is if a Mars exploration sequence of missions is something like 4 crew on every other Mars opportunity, that means something like 10 seats per decade are up for grabs in a Mars exploration plan. Now, maybe it'll be a little bit more than that, but we're talking about a pretty small number ultimately. So earlier today, Artemis was asking whether a Dutch male astronaut would be too big to fit in the spacecraft. I think really the more important question is a Mars spacecraft too big to fit in the Dutch budget? And ultimately, if there's a very small number of seats, if there's a very limited number of seats, and you are looking at this from the perspective of a space agency with a small budget, what are the odds you will be able to have a big enough contribution to this to get one of those seats? So one of the reasons that exploring the moon on the way to Mars is attractive to those other countries is that it is so much easier and so much cheaper. Now, whether you go to distant retrograde orbit or L2 or L1 or a rectilinear halo, there's lots of interesting orbits we can debate about among the orbital mechanics community in this room. But these orbits are all surprisingly easy to get to. They are much easier than low lunar orbit. They are much easier even than geosynchronous orbit. And that means that multiple countries can contribute things, in some cases that they already have, or at least that they can afford to develop, and have a substantial role in these programs. And an orbiting outpost around the moon in whatever orbit it is can contribute to a variety of goals. So even though these countries don't all agree on exactly what we should be doing next, this can be a useful thing to do, whether your objective is to play around with asteroid material that you've brought back, or to practice and demonstrate life support systems for Mars, or to operate robotic systems on the lunar surface. So we can get a lot of different stakeholders, different people with budgets together, and even though they don't completely agree on all of the objectives, they can all see something that works for them. So there's essentially 2 ways to conceivably pay for this outpost. One, as I talked about, is to get lots of different partners together to split the bill. This is a concept that's been worked on by an international industry team. It includes Boeing, so Matt and Keith have been involved. It includes Thales Alenia, it includes Mitsubishi, McDonnell Detweiler from Canada. What you see here is a relatively large habitat module in the 25-ton class. This is a Russian element derived from their space station modules. This is the size that would take a dedicated SLS launch. So there's a Russian module, there's an American spacecraft with a European contribution, that's the Orion. There's a Japanese logistics vehicle. This is a derivative of what they're working on for ISS cargo servicing. There's a Canadian arm, and then there's a robot roving on the lunar surface that might be Canadian or Japanese, might be launched by any of a number of countries. Now, the point is not to argue that this exact solution is what should be built, but to show that there are some technically plausible and politically feasible approaches that could be worked out here that would fit within each of these countries' budgets. And we've been working together at the level of figuring out details like how do we orient these modules so our solar arrays aren't shadowing your solar arrays, and who's transferring power from one module to the other, and who's actually driving which module is providing the RCS thrusters and the attitude control here. So we believe that this is a feasible kind of mission to do. But we've talked about this a lot in other forums and other conferences, so I don't want to go into a lot of detail about it here. You can ask questions in the panel session later if you're interested. Instead, what I want to show you is something relatively new, and that's the other way to pay for a outpost orbiting the moon, which is to sneak it into somebody else's budget line item. So we've talked in this conference a lot about it would be desirable not to have single-use items or point designs. Most of the discussion of commonality has been about making all of the future elements common together so that you only have to have one new budget line item to build those. I've got a better trick which has 0 new budget line items, which is to sneak this in an existing program. And that is the ISS cargo resupply capability. So as you probably know, NASA is recompeting the ISS cargo contract for future ISS logistics beyond 2017. What we have proposed is a tug spacecraft. So this is a long duration spacecraft tug here on the bottom that's derived from our interplanetary spacecraft, which brings up new cargo modules shown in the upper right here to space station and then disposes of them. So that's a Thales Alenia module derived from the ATV pressurized module in the upper right there. It's relatively large compared to the existing cargo capabilities. Essentially, it duplicates the capability that ATV had for logistics. It can also carry external cargo, unpressurized cargo, and then fluids. So basically what we're suggesting is you could take a spacecraft element that could be developed for ISS logistics, and you can launch it to deep space and use that same spacecraft as the destination for the crew to go for at least the initial visits. Now, it's pretty common in the space industry to tell you that we can just take this one thing we developed over here and use it for a totally different purpose, and it won't cost any money, and it'll all be great. It never quite works out that way. There's always differences, and certainly there are some differences here. But again, this is a spacecraft that is already basically designed from our interplanetary heritage, so it can handle the environments. It's designed in the cargo application to stay orbiting near space station for years at a time. It's not a short duration vehicle. And then the habitat element is designed to be relatively large to carry bulky cargo. So, and of course, we're highly motivated to have a destination for Orion to go to. So we think that we can, in fact, build a relatively modest investment into this ISS cargo vehicle and turn it into an interplanetary habitat. It's important that this be big enough to be useful as a habitat. So just to give you a sense of scale, here's the mock-up we're working on. This is ISS module diameter. That's important to us for the habitat application because there are certain things we need, like I mentioned, proving out advanced life support. So the modules on ISS that have those life support systems currently today are rack-sized. Think of this as the equivalent of a really nice refrigerator in terms of size, but also power. It's not a particularly small element. There's also things that we need that are fairly bulky. For example, Robin showed earlier the exercise equipment on the space station. That is not small. We need the room to put something like a treadmill or the resistive exercise equipment in there. And then, of course, if you're going to be in this for months at a time, you want some room to stretch out, and you need room to put the consumables, the extra food, water, clothing, and so forth. So it's important that it be big, but also that it not be too big. And the module that we've sized is basically just the right size to fit either in the co-manifest capability on SLS in terms of geometry and mass, which, as Matt alluded to, is really useful because it means you get a sort of free launch with every Orion flight to carry these logistics elements up. But it's also small enough to fit as a dedicated payload on existing and planned commercial heavy lift launch services. And what that means is that we could conceivably offer this as a commercial or industrial capability to NASA without relying on NASA for the launch service. So here's an impression of what that would look like with a cutaway view here. The volume is about twice the size of the Orion pressurized volume. That means when you put the two together, you have a total volume that's 3 times the size of Orion. One of the things that I think is very important, regardless of who ends up building this, whether it's one of several American companies or international entity, and whatever design you end up with, is that it's important, as Matt alluded to think about how these kinds of habitats or outposts work with the Orion spacecraft. Orion's a highly capable spacecraft designed to keep the crew alive in this environment for a long period of time, so it has things like the toilet, it has the galley, it has a great carbon dioxide and humidity removal system, so there's no reason to power that down and have a duplicate system in the outpost that you power up. Let's share that capability across these modules. And at least initially, that means you can keep the outpost for the first several flights to be relatively small and inexpensive. Now, at some point, you want to grow this into a bigger capability. And I think this is very, I hate to use the buzzword synergistic. I think this works well with something like a larger element for a habitat that comes along slightly later in the mission sequence, perhaps in the later 2020s. Here's just a brief functional summary of some of the things we would consider in terms of how do Orion and a habitat element work together. For example, Orion is designed for low Earth orbit and low lunar orbit, which means it's expecting to be eclipsed for roughly half of the time. If you're in L2 or DRO where you have almost no eclipses, that means we have several kilowatts of extra power. It's convenient that that's available when we bring the crew up to the outpost, because most of the time the outpost is dormant. It doesn't need very much power, but when the crew is there and you're running the life support systems and you have a lot more things going, that's when you need the extra power. So we're looking at what are the power budgets in different modes, what can we share across that interface. There's also potentially some extra thermal heat rejection capacity that we could take advantage of. I mentioned exercise equipment. Another thing you could think about is where does the crew sleep? So obviously there are 4 sleep stations in Orion, but there'd be a little bit more privacy and elbow room and perhaps quiet if you split the crew up and had some of them sleeping in the outpost. Radiation is an interesting one. Orion is already designed to handle a fairly severe solar storm. So Orion has a lot of radiation protection built into it. That means that you don't have to add additional shielding capability to your outpost, but it probably also means that there is room for those two things to work together. So we're looking at how do you lay out the systems in the outpost such that they also shield Orion, or even how do you carry supplemental radiation shielding that you can leave in the outpost and carry over to Orion if you need it in a solar flare. For example, there has been investigations on how do you take all that plastic packaging that's used in the logistics and cargo and sort of compress that down into bricks that you could use as plastic radiation shielding. You could leave that in the outpost and build it up over multiple missions, and you end up with a solution that gets more radiation protection than either Orion or the outpost alone would be able to provide. EVA is an interesting one. There's some discussions about what EVA capabilities do we need for these missions. If you just need a contingency EVA capability for emergencies, such as to fix something, then Orion is already designed for that. And particularly for the asteroid redirect mission, NASA is working fairly hard on figuring out how you do spacewalks out of Orion. So we have things like places to have handholds on the outside of the spacecraft. The spacecraft is designed to be kicked by astronauts. It's designed that you can depressurize the crew cabin and still be able to operate the buttons on the control panel with fingers that have gloves, spacesuit gloves on them. But Orion's not really how you would want to do spacewalks if you were going to do them many, many times in a routine way. So if you wanted to do something like do multiple spacewalks to explore this asteroid that you've brought back, then you might actually want an airlock on the outpost. So those are the kinds of engineering topics we're going to be getting into in the next step studies that were awarded just recently. So with that, I'll leave you with a closing thought that is short and brief enough to be tweetable. And that is that regardless of who builds this, that we think a small outpost orbiting near the moon is not only a good idea, but an affordable idea for the next step beyond ISS.
Well, thank you very much to our panel. Yeah.
I don't want to confuse people.
No, don't want to confuse people. No. Well, I'll see if I can manage to put it back up without knocking it off. I think that's the challenge they leave us with. So I guess I'm adept at that. So we have a little bit of time for some questions, so we'd like to open it up at this point. Anybody have any questions? Yes, sir.
Lunar outpost, we talked about possibly
There's been a lot of discussion about that. In fact, the discussions we've had with the partners have been very much along that line, potentially the partners providing a reusable lander. Yes. Right now, it's the current ISS partnership is principally who we've been talking to. So that would be the Europeans, the Japanese, the Canadians, and of course, the States. So, I mean, that's very early in discussion, along that line. One of the other things, that we've had brief discussions on, I mentioned earlier on, we're proposing that we do some excursion missions, we do some transits, deeper into space. One of the things that we've notionally discussed is the idea of that we combine one of those missions with a surface mission to the moon, since that's one of the things that's very much in the partner's interest. And that would be very much, an analog to a Mars mission where a transit would occur followed by a descent to the Mars surface. That's very early in discussion, but but these are the kind of things that are in play because we have partners. So, yes.
You're addressing orbiting the moon, you're addressing being on the surface of the moon. What about L2? What about a hub for infrastructure and propulsion system?
Yeah, the families of orbits that we're looking at in the lunar vicinity are not necessarily they're more in the Earth-Moon system for the most part, like DRO, while it's a lunar orbit, there's other orbits like some of these near rectilinear orbits that are, really in the Earth-Moon system. So we're looking at, that whole family of things, and one of the things that you could do is leave infrastructure for servicing, for a system that's transiting. I think one of the things we'd have to trade on that, though, is which is more efficient, to have a platform that's also something you have to maintain to service something that's coming back. Or is it just more efficient just to fly things right to the thing that you're trying to service and, service it at one? So it's certainly a possibility, and we haven't got to the point where we've nailed down what the best approach for that is.
Well, certainly for the lunar step, I can see orbiting something, but if we're talking about Mars, if we're talking about this is the step which is going to the moon, and using an L2 or some similar location for integration and resource support and everything.
Mm-hmm.
You haven't addressed any kind of infrastructure.
Well, I don't think that's one of the things I think I mentioned is that we don't necessarily need an infrastructure for that. If you can, much like the Russians, for example, when they put Mir together, they basically assembled it in building blocks that were kind of standalone spacecraft. They didn't have an infrastructure per se other than the platform they were assembling. So I think conceptually we're thinking more along that line for any infrastructure that we're building up in multiple modules in cislunar space would be more like that model. I don't know if I've answered your question or not.
I'll interject on that.
Please.
In some of the scenarios that we've looked at for cislunar space, we started off with something like a service module, the way we did with the ISS, and then followed up with a docking node so that there was multiple places to dock. And those two items you would not want to take to Mars as part of the Mars vehicle, and so they could stay in place. And part of the thinking is that there are international and commercial interests that might want to use that same infrastructure and leave their components there too, and that would be resupply systems, maybe another habitat that stays there from the internationals. Maybe the reusable lander can go from there down to the surface and back and stay there and be serviced at that point. So that kind of thinking has been on our minds as well in other studies. Yes.
Can an Orion or an Orion derived capsule or hardware be used for that?
It could dock to the docking station as well. Yeah, the docking node, sure.
Okay. Yes, sir.
Given the time frames you're talking about creating such habitats, I'd be interested in hearing the panelists' views on a Mars or Mars-Venus flyby in the early 2020s.
I'll start. I guess I have two answers to that. It's technologically possible, though we're getting right now up to the bitter end, I would say, of being able to put that together as a program. But the other side of that is the budget, and whether you're really ready to commit the budget to that, and how that all plays out, and what gets paid for and what doesn't get paid for. But for a Mars flyby mission in the early 2020s, yeah, that would be doable if we started right now and made a large commitment to doing it.
Yeah, I think one of the challenges programmatically is, as you're alluding to, there's this 15-year cycle of how easy or hard Mars is to get to, and so the landings probably happen in the mid-2030s. There's an opportunity to do a flyby 15 years earlier in the early, 2019 or 2021. But not only are we sort of running out of time to do that, but that 15-year gap and the fact that we're not really ready to design the Mars mission spacecraft, the Mars landing mission spacecraft today, means that whatever you might rush to build in a crash program to do a Mars flyby very soon is probably not very applicable to what we would actually do when we get ready to do a Mars landing.
A dead end.
Yeah, it would be sort of a dead end. I mean, it would be useful in that it would persuade by evidence, persuade people that you can in fact get to Mars, or at least, let me rephrase that. It would provide definitive evidence one way or the other. We can hope that it would be positive evidence. But, in terms of actually developing the systems you would really use for a Mars mission, it probably would be a programmatic dead end. So it wouldn't be
Now, that's
like
the boring
Apollo 8.
engineering answer.
Yeah.
Is that the hearts and minds answer? I mean, we
Yeah,
need to
right.
get a different panel.
Yeah.
Right?
Harley got a question.
Yeah, an observation, and a question. First, an observation about international partners. It sounds a little bit like it's possible partnering to go to the lunar surface. It sounds a little bit like a warning that actually was it your warning, Skip, that we created an architecture, and if there's a problem, international partners can step in. Maybe Josh, whatever. Good point. You have first-hand information. Mine is definitely second-hand. When some folks have presented to potential international partners who likely bill for a lunar survey, particularly international partners whose spaceflight program budget is shrinking, bill for a likely sortie type orbit capability of the surface, they blanch back away. They would like to find other connections to pay for that. Always pointing to somebody behind the tree.
Yeah, well, they would like their international partners, i.e. us, the United States, to pay for it. So,
Well,
so I
but let me add to that if I may.
So I do have an unrelated question.
Okay. That's, you always get into, when you're having international discussions, you always get into the discussion of who wants to blink first, right? For lack of a better term. Everybody comes in and says, what are you going to do? Well, you tell me what you're going to do. And so, we have some notional ideas from some of the discussions we've been having of who's interested in what. Now, one of the challenges is almost all of the partners, including us, are basically on a budget cycle right now that's going to culminate over the next couple of years. All right, okay. The Europeans, for example, their next ministerial meeting that would allow them to do any kind of a new start is the fall of next year. The Japanese are, on similar kind of timelines. We have maybe something next fall that might affect our budget, horizons. I don't know, perhaps. But at any rate, so right now, we've developed, one of the things that we've done is we've developed a matrix from the top level of a spacecraft down through all the systems, and asked each one of the partners to, as a starting place, to put in what they're interested in doing. We're in the middle of putting that together now, and that's helping frame, the discussions of who might provide what. And in addition, even at the macro level, we have some idea from each of the partners about things they might be interested in. But that's very early in that discussion.
The Apollo lander, for the whole system land, not the getting to, not the
Yeah.
Apollo was in 2014 dollars was $30 billion.
Yep.
Probably do it for half things like that. So I just I read about the economies of Western Europe, Russia. I don't see the time frame we're talking about.
They're not the only people on the planet.
Okay, let me ask my
So
question.
Harley, if I could follow up on that question first. So the scenario that's been presented essentially is that because NASA is not going to go to the moon at all, to the lunar surface, excuse me, to the moon, right? The moon is that what they've basically said is, well, we'd be willing to take other countries or commercial entities to the vicinity of the moon, but they're on their own getting all the way down. So, right. And I think you're correct that investment, that complexity is more than any of those other countries want to bite off if they have to do all of that.
Yeah.
It would be a slightly different answer if we said, we're willing to split the cost with you. They might be willing to pay half of that cost, for example. But the other issue is that NASA does not even officially have any plan beyond 2021. There is no mission beyond EM2. There is no official adoption of this outpost in NASA's plan. So if you were the head of agencies in another country trying to decide whether or not to invest in a lander that would be completely dependent on NASA following through on their portion of the deal, you'd be pretty skeptical, or at least you wouldn't be sufficiently confident to commit the enormous investment that would be required. So I don't think NASA and the United States can get out of a leadership role in this, essentially.
No, it doesn't. And further, if I could add to that, though, you know, the kind of construct that we're talking about here does not rely on us going to the moon,
Right.
to the surface of the moon.
Oh, that's true.
Right.
Let me ask my question.
Sure.
I don't want to.
Your other
what
question.
we've come for was. So question is, and this is for everybody but Josh. No, for good reason, because Josh had a couple of nice charts on what you might do with a habitation system in the vicinity of the moon. And Skip and David for some time. It's awfully, why not do this habitation system in Leo? Away from the space station, but in Leo, much less expensive. But you can do all with the exception of what Josh might have. You guys can do everything that you wanted to do, that you listed in Leo.
So I think what Harley just said is, other than my answer, all other answers are wrong. So good luck.
Well, I agree with your answer, what should I do there? But for the other three,
Okay, from my perspective, what I like about the distant retrograde orbit is that it's a place that I can return the habitat to for retrofit and refurbishment. And it's quite difficult to do that, I am told, as far as bringing it down to the Leo vicinity and when you're coming back.
just never launched up.
I'm sorry.
Just do the whole thing.
Oh, well, the second point there is that we need to be in a deep space environment for the radiation protection. I mean, the radiation issues in particular, and so the distant retrograde orbit provides a number of benefits in that you're in the right environment. You're in a place where you can actually do the retrofitting whenever the habitat comes back, and you're in a place where you can possibly share with other missions that would be going to the moon, as far as dealing with the internationals and potential commercial investors.
I'm going to go last if you have a comment.
Okay. I'd agree with the radiation, definitely. That's the huge difference between, sorry about this, lectern. I feel like I should be talking to you. That's the huge difference between Leo and the deep space environment. You're not going to get that test in the Leo environment and not really have that assurance. But beyond there, I think we also learn a lot just by operating in the environment that you want to be in. And it's the case of the unknown unknown, to paraphrase Don Rumsfeld. We don't know what we don't know out there. And so actually operating it in that environment may teach us things that we really just will never get out of Leo, since we do think Leo the way we've always done things in Leo. It may be the communication lag. It may be some part of the way the crew interacts with the ground being that far away. There are just things there that are going to be fundamentally different. And so in that operation of the vehicle itself and in the operation of the systems in the vehicle, I think you learn a lot more by really being where you intend to go in the long term.
Yeah. Finally, I would extend that argument, right? It's, if you carry that to its logical conclusion, why am I in space at all, right? And so the real reason on this is, like any other destination you go on, it makes no sense to go from the harbor that you know and try to go around the world on the first attempt without at least trying to go a little ways out and understand what the implications of that. Some of those things you've already heard, right? The other things are, we know infinitely well how to do mission operations in low Earth orbit with crews. As we get further into space, we have the comm lags. It's going to be harder and harder to have that day-to-day hand-holding or hour, minute-by-minute hand-holding that we have in low Earth orbit. There's always, I hate to put it this way, also the crutch of, hey, if something goes wrong, I can just jump in the capsule and go on the ground. So if we're ever going to go deeper into the solar system, we need to take incremental steps, and we know how to do low Earth orbit operations. We need to take the next step, and cislunar is an obvious place to take a step beyond where we've been. Okay, and I think I had one back here first, and don't let me forget. Yes, sir? After the BAA, is that what you're asking? Oh, you're talking programmatically now, right? What are we going to do with that, as you're asking, right? Okay, I'm going to give a really vague and answer that's not going to answer your question, right? Because I think it depends is the short answer. I mean, the BAA is constructed in a way that it could both gain us knowledge as well as lead to the opportunity for further awards. I think a lot's going to come out of what products we actually get and how successful that is over the next year of the initial period of performance. So beyond that, if we're looking at, how we're going to get these systems ultimately, that's something we have to work out. One of the other secondary tasks, part-time tasks I have in this little assignment I'm working on, is to work on a proposal for what acquisition strategy we'd ultimately use for this kind of system. And when I use acquisition strategy, some people get their shorts in a knot and say, "Oh, you're going to do a procurement?" Oh, well, no. I mean, that could include providing by the IPs, some kind of public-private partnership, some, traditional procurement, some combination thereof. We have to develop that. So that's a work in progress, and so that's my vague answer to your question of what's next. So yes.
One answer to this gentleman's question is one idea that Josh had reminded me was that no latency teleoperation of assets on lunar surfaces of good mission.
Yep.
There are a lot of international partners that can put rovers on the surface and they can base the South Pole. And he's an opportune place to do no latency teleoperation. That could go on for years and it would be very valuable. So Leo wouldn't provide that. So he's got a good answer. He just didn't have time. He had plenty of hours. That's what he said, that with the exception of Josh. That's why I didn't want Josh to answer. On distraction from regular would be a good teleoperated package.
Yeah.
Yes. Yes, you had a question?
Yeah, well, use buzzword, but, and forgive me if this is the naive section of the past, but James Webb is what the L2, right?
It's
Earth, Sun, L2.
Sun, yeah.
But nonetheless, there's some concern about the maintenance for that craft.
So there has. There's actually a joke going around that SMD is putting James Webb at Sun-Earth L2 specifically to get it as far away from the astronauts as possible, but I don't think that's quite true. No, we have thought about whether you could service James Webb with Orion, and especially if you have some sort of small habitat with additional consumables, we can get astronauts out to the Sun-Earth L2 point, which, as somebody said, is distinct from the Earth-Moon L2 point. But in terms of the duration and delta V required to get there, it is feasible. I think that there is a mechanism we can attach to on James Webb, but overall the spacecraft is not designed to be serviced. So unlike Hubble, it doesn't have easily accessible doors and astronaut handholds and instruments that are designed to be taken out and replaced. So it's not something that we would plan to nominally do, but if something were to happen, I suspect there would be a more detailed study of could you figure out how to fix it anyway.
Certainly, we've demonstrated on Hubble that we've replaced things that weren't designed
to be
for that
replaced.
capability, so, yes.
Well, I think, we're here at the Humans to Mars Summit, and the patience of the public for the space program, it's declined a lot over the years, because we're not doing golden things. if you propose bold things like not treating the moon as if it's radioactive, but going to it, or, learn how to live on Mars by learning how to live on the moon, and actually staking out a plan to go to Mars. As you said, we don't have anything on the books beyond the M3 except for, vague definitions of an asteroid or a thing. At some point, if we're just doing operations, running robots, okay, we're going to run the robots from this orbit or that orbit, it's going to exhaust the patience. And we don't live in a vacuum. China will be doing moon landings in the 2020s, perhaps even by the early 2020s. They'll be doing a lot of other sort of landmark things. And if we are doing the small things and not arguing for a larger budget to do the things that will keep the U.S. as the leader in the space program and high technology for yet another generation, then we're going to be playing second fiddle. I'm not advocating partnering with China. They'll just steal our technology and then kick us off the boat. But address that. How will we actually get to Mars, landings, footprints, and the same with the moon? If we are only going the very narrow edge of, well, we're not going to ask ever for a dime more. We're not going to go Neil deGrasse Tyson and say double the budget. Much less Apollo and 4% of the budget. Tell me how we can break out of this mold that will lead us spiraling downwards and downwards and downwards with carrying public interest with it.
I think that I'm going to give you two parts. One is it's hard. We live in a generation where I think that a lot of people are more interested in when their next iPhone comes out than what's going on in world and national, politics. That makes it challenging for us. So that makes it harder for us than, in the days of Apollo, it was easy. We have this geopolitical threat. We need to respond to it. We're going to the moon. We don't have that today. But at the same time, I think if you look at what we're trying to do and some of the themes that you've heard from the NASA folks over the last couple of days are we need to provide a program that shows that we're incrementally moving outward from the Earth and we're doing something that's substantive. If you look at the EFT-1 mission that Orion just flew, that got tremendous public interest, and surprisingly enough, if you think about it, for those of us that are technical guys, we look at that and go, well, we needed to do that. It was a couple of highly elliptical orbits, but that's certainly not beyond our capabilities and it's a challenge. We need to do that, prove technically. That doesn't excite people. What excites people is phrasing it in terms of it's the farthest a human-rated spacecraft has been in 40 years. People got excited about that. If we can take this is why you hear you'll hear more and more from us, the themes of going farther and more on more complex missions on every attempt that we make. Because if we can do that, then every one of those is the farthest point that humans will have ever been. And it's an incremental step on the way toward farther places in the solar system. And that's the way I think we need to couch this, is it's not just a bunch of, part of it is we have to be able to demonstrate that we're checking off the things we need technically to be able to be Earth independent ready, but that also has to be phrased in a way the public can get their mind around as, hey, it's progress, it's farther, it's challenging, and these are a big deal and why you should be excited. That's really what we have to do.
Thank you. I agree with you. I believe that we need to do more to work on if the president proposed doubling the budget, it would probably happen. The budget's been declining and, dramatically since the shuttle days, much less the Apollo days, and we become less able to do the things that will really carry us forward and keep us the leader in space and high tech. So I hope to see that, that sort of ideas coming forth that will carry us to those footsteps that will transform the world.
So I'm going to take a little bit of a contrarian perspective. I think that there have been lots of studies that have suggested what we could do if only the taxpayers would give us more money. I mean, the Augustine Committee did that the NRC panel did that. There have been lots of studies by people like us of what could we do if only there was more money. But, well, just a second. But I think it's important that as responsible adults and good stewards of the taxpayer money, we also have to answer, what can we do if we don't get more money? What will we do if we only get the money we are likely to get? Because that's the most likely scenario. And it's not that it hasn't occurred to anybody to ask for twice as much money in the NASA budget. It's that the space community has not really explained or found a good answer that would persuade either the leadership in Washington or the American public that it's worth spending twice as much money on NASA. And part of the problem is that even within the space enthusiast community, we are very divided. There are two different conferences in Washington in the next few months about how we should send humans to Mars by two different Mars advocacy organizations that don't get along very well with each other, right? They agree on 99% of what matters, and they can't manage to have one conference. Now, then you've got the folks who think we should be doing lunar exploration. They agree on 98% of what matters with the folks in this room, but have a slightly different destination. And that's just all the people who agree that we ought to be doing human exploration beyond low Earth orbit, right? Then you've got the folks who agree we ought to be doing a lot of exploration, but it should be with robots primarily. And then you've got the people who believe we should be doing a lot of exploration, but it should be whatever commercially motivated or settlement-minded things we should do. So when somebody says we ought to spend twice as much money on NASA, but we in the space community can't agree on what we would spend that on, I think it's very clear we don't yet deserve that extra money. So we need to come up with responsible, effective ways that we all agree on how to use that money before we go ask for it. It's my personal perspective.